Okay, so welcome back. So we've generated the mesh, and now we want to focus on the mesh input, but also the other inputs that we're going to need to get our Python script working. So just a couple of things. I've been a bit bad. I haven't been saving myself, so I'm going to start trying to remember to save more often. And then we know that the Python component, so that's what we're going to use, is this one here that we're after, Python 3 script. And providing we've done everything correct previously, that will just go on fine. If it is going to try and load Python because it hasn't done previously, or any of the user packages, you'll see a little kind of progress bar at the bottom of this component. So that'll let you know whether things are going well or not, basically. So let's double click, and that brings up our script editor. So we can see the example script is in there. So I actually want to just get rid of that. And this is the stage that I'm going to just use the script that I made available to you in the notes and the slides, or it's up on Blackboard as well. So in fact, I'll just do Control A to select everything, and I want to copy all of that. So I happen to use TextPad, but this will open fine and do the same in Notepad or any text editing software. And then I'm going to go back into my Rhino and Grasshopper here. And so here, I don't have the option directly to paste in, so it's Control V will allow me just to paste everything in. I'm just going to save that within the component. It will immediately chuck up some issues because I haven't yet developed my input and output options, but we'll just save that for the time being and shut this now. So we will continue to have issues with this component basically until we build all of the input that it's requiring for the script, and actually we need to define the appropriate output as well. So the list that we have, we're going to have E for Young's modulus, and actually the way I've set it up, we require list access for that. We're then going to have A for the cross-section area, and again I want list access for that. And actually both of these, because they're numbers, the type that we want them to be is a float. So I'll just do that here. So this obviously is a little bit laborious, but it's just the sort of system we have to deal with in order to make sure we're getting all of the information correctly, going from Grasshopper into Python, and then obviously going back from Python into Grasshopper. So I'm just going to add quite a few potential inputs here, and then we can continue working through. So here I've got my second moment of area, which I'm leaving labeled as IYY. Obviously it gets simplified to I in the script. And again, that will be list access and float now we want. So the next one that I want is node numbers. So, or actually before I get to them, I have deliberately decided to keep getting the total number of nodes and the total number of elements outside. So we've got node numbers there, and this should be an integer. And actually, although I may end up going back and having to edit this, at the moment we're going to say that will be item access. So if I've got my number of nodes, then I want the number of elements as well. And again, we'll leave that as item access for the time being. but type hints, we will change that to an integer as well. So now I want my element nodes. So this is probably the most important input in terms of this is how the capital K matrix is going to be constructed, is based on this information. And actually this is unusual, so this needs to be tree access. But again, we'll just hopefully not need to come back and correct this. These should all be integer values as well. And then something that we could calculate within the Python script if we inputted the nodes with their coordinates as points. But instead I've decided I will calculate it outside. So we need to know the element lengths. So that's important. Again, that features as a term in the element stiffness matrix and also the system stiffness matrix. So that will be list access, and we want type hints. Those will be floats. So I'll just zoom in to add a couple, well, 3 more. So we've got element lengths, element angles is the other information that we need. So obviously to go from K for each element to K dash, we need the angle. So again, this will be list, and again, this will be float for the type. And then the last 2 things that I'm going to put in. So I'm just going to call this point loads. Obviously I could have called it node loads. If we were calculating nodal equivalent forces, we could put all of that information in here, and I'll go into the exact format that we want for that in just a minute or so. So again, that is list, and the way that I'm going to introduce this is actually as a string with a particular format, and that's dictated by the Python script, but it will also dictate the way that I'm going to define it outside in Grasshopper. And then the final one that we want, just changing its name. So we're going to call this one boundary conditions. And again, this needs to be list because we do want to be able to apply more than one boundary condition if necessary. And again, it's going to be a string, so it's going to be processed in a particular way. So it's still red because obviously we haven't put any information in here yet. Something that I've done that I just kind of recommend. So because you might be sort of playing with the script a little bit outside, I recommend just putting in what are called relays. So these are just kind of stop gaps along the way. I mean, you could define each one of these as the data type that we're going to use. But what it allows is basically just for the Python component to sit nicely in the middle of all of this. So I'll just finish off doing these. And then we'll be able to connect things basically to the other side of each of these relays without obviously affecting what's going on in the Python component. So just got 4 more, 3 more, 2 and 1. I'll just add all of these. And then the final thing I'll do just is line all of these up. So I want to just line them all to the middle there. So that will do that there. Okay. I am just going to add the output as well. So in terms of the output, I'm going to leave this one out here. And I'm just going to come in, I'm going to change A. So for A, I want my node displacements, which I've called node disps. And I'll pop a relay on that as well. So like so. And then actually I do want another output. So I've just called them beam forces in the output here. But obviously I mean beam end forces for those ones. Okay, and I'll pop my final relay on there. And although this is very slightly different to what I've done on the canvas, I'm going to select all of them and group them. So middle click and group, and I'm going to just say that this is the Python script to construct K and solve for U and F. Okay, so we have that all set up. So now really what we want to do is just make sure that we've got the appropriate input for all of these. So I'll just come to that in a second. Okay, so our number of nodes and number of elements is very straightforward. We just want the component list length for each of them. So there we are, and list length again. And what I need to do, so again, I can either go back to where I originally defined it, or I think I will go to these items in this case. So that's going to be my list length of nodes. And then this one will be my list length of elements. So I'm just going to group them, middle click again. I'm just going to label that. Need to select the group. So number of nodes and elements there. And then obviously this is one of the first components, so I'll just move things around a little bit here. So this is going to be one of the first components where I can feed these in. So obviously I've got the number of nodes can just go in there, and then the number of elements just goes in there. So I may as well sort out some of the other information that I need here in terms of the material property, so Young's modulus, and also obviously the cross-sectional property. So what I'm going to do is I'm going to assume that we have a rectangular cross-section, but I'll define Young's modulus first. So I'm going to have a panel here, change it to multi-line data as usual, and I'm actually just going to label the panel. So that's something you can do with panels. So I'm going to say this is Young's modulus, and although obviously it's unitless, I do just want to put in units to indicate what I'm expecting them in. So megapascals or newtons per millimeter squared there. And I'm going to assume steel. So we have 20,500 is the value for steel in megapascals. So we'll just tidy that up a little bit. So just correcting this, so of course, because the value of Young's modulus for steel is 205 gigapascals, in terms of megapascals, it will be 1,000 times that. So 205,000, that should be. So we'll just click OK there. And then I'm going to put in my breadth and also depth in a second for the rectangular cross section. So again, we'll convert that to multi-line data. I'm just going to call this then B, and that should obviously be in millimeters. Put another panel, we'll make that D, so the depth, change it to multi-line there. So D in millimeters as well. So I just tidy these up a little bit. And initially I'm just going to assume that each of these has a dimension of 10 millimeters, like so. So obviously I can then just directly calculate the area. So to do this, I'm going to use an expression, and I can clear out the sort of formatting information, and obviously the area is just B times D, but I need to change the input to make sure it understands what is B and what is D. So I'll relabel them, and then I'm just going to change the output to A so we know it's the area. So I can put those two together, and I'll run A down there. I'll run my Young's modulus down there. And then obviously the other expression we need is the one for second moment of area. So I will cut that. So we know this is going to be BD cubed divided by 12. I probably don't need to, but I'm just going to put the brackets round to make sure this is calculated correctly. And again, need to change that to indicate it's B as the input, and this to indicate it's D. So I can bring these in like so. Again, I'll just try and tidy everything up a little bit. Change the output there. I'm going to change that to IYY. So we'll just hover over. They both look fine. So I can connect that in like so. And then I'm just going to group everything up here. Again, trying to keep everything reasonably tidy. And I'm going to say material and cross section properties. Okay, so we'll just pause there briefly again, and what I'll do is when I'm back, I'll just explain how we're going to use the information about the start and the end nodes to allow us to define that aspect, and obviously how we're going to calculate element length and element angle as well. Okay, so I've just tidied the canvas up a little bit, but now what I want to do is I want to get the information for the start and the end nodes of each element. So that is given by this index here. So I'm going to use a component called merge. So we will run that list in there and run this list in here. But what I actually want is I want the data to be individual items, so that the start node and the end node, they're the bits that get combined, rather than the whole list of start and then the whole list of end nodes. So the way I can do that is I just need to graft the input, so that what comes out here is a series of just two outputs basically for each entry. So if we have a look, we can see now we have 0, 1, 1, 2, 3, 4, 4, 5, and so on. So I don't need to keep that information, but what I am just going to do is I'm going to do something known as flip matrix. So basically that is just getting it in the format that I really want it in, which if we have a look, so what I now have is effectively it is two lists again, but the branch structure of the tree is the one I want. So in location 0 are all of these numbers, so those are all of the start nodes, and in location 1 effectively are all of the other nodes that I want. So it may appear to be just sort of a bit of trickery in terms of the data structure, and to some extent it is that, but it's getting it into the form of these two branches that we can then use straightforwardly within the Python script. So I can connect that up to element nodes, is the one there, and I'm just going to label these two components. So we'll group them and say defining the start and end nodes of each element, like so. And then we want to calculate the element length and also the element angle. So the way I'm going to do that is I'm going to get a vector in the x direction, so this is the unit x, and I also want to define a vector based on 2 points, so I can get my points from those closest point in the point cloud ones, so a and b, like so. So that gives me a vector out. It also actually gives me a length, so that's obviously I can plug that straight in from there, so that will be my element length. And what I want is basically the angle between those two vectors. So that's just the angle component there. So I can feed in my unit x and then the vector that I've defined between the nodes, and so that can then feed in as my element angle. Obviously here, because it's just a horizontal beam, as we would expect, all of the angles are 0. So that's just a little bit of reassurance there. Again, I'll just group this and I will call that calculating the element length and element angle. Okay, so we are almost there. The final step is just going to be to set some conventions to define the point loads and the boundary conditions. So I'll just pick up on that in a second. Okay, so for the point loads or the nodal loads, the convention that I want to adopt is I want to be able to give it a node number, and then I want to be able to give it a load in the x, the y, and the z. So these are obviously the global axes. So x and y would be forces directly, and obviously z, because that's the axis that we're looking at rotation about, that would be a moment if we were defining it that way. So I can set up a panel like so, and because I know 8 is the unique node number at the end, and remembering that we're looking at a cantilever, I'm just going to say, okay, at node 8, I want a load or a force of 0 in the x direction. I'm just going to say -1 Newton effectively in the y direction, so that'll make it down by having it as minus. And obviously I'm not applying a moment, so I'm just going to set that as 0. doing what I normally do, so just make that multi-line data. And then I'm immediately just going to put this into a group, and I'm going to call that group point loads, and basically this is just some text to remind me how everything's put in. So we have the node number, then the load in the X direction, then the load in the Y direction, and then finally any moment about the global Z axis. So that's everything defined there. I will just connect that in. We should see that change into a nice line, or at least not a red line anymore. And then the final one, so the way that I would like to be able to define boundary conditions, a little bit similar to loads, but this time what I want to do is I want to give it a node number, and then it's a binary consideration. So if it's 0, that means actually I don't want to constrain that boundary condition, whereas if it's 1, I do want to constrain that boundary condition. So this is quite a sort of flexible approach, and obviously it means that I'll have the node number followed by 3 either 0s or 1s for each of the degrees of freedom at the nodes. So I know for my fixed boundary condition at node 0, I want to fix it in the X, the Y, and also from rotation about Z. Again, I want to make that multi-line data, and again I'm just going to group that and give the group a name. So I'm going to call this boundary conditions, and the nomenclature here, so node, and then basically I'm going to say, okay, that's UZ, so that'll be 0 if we're not, or rather UX, so that'll be 1 if we're fixing it, UY, and then finally RZ I want in here. Okay, so if we connect this up, now we can see all of a sudden it goes nicely just grey rather than red. So what this means is that our Python component is doing something. If I look, we can see we've got a long list of numbers. So we had 9 nodes, so 9 times 3. That does appear to be the correct number of numbers at least. And another long list of numbers. So we have 6, for the start and the end forces on each beam element. So then 8 times 6 gives us 48. So again, at least we have the correct number of entries here. So the final part then of these video explanations is we're just going to process this data either to produce displacement plots or to produce the diagrams that we were referring to. So in this case, obviously, it will be the shear and the bending moment diagrams.